Sit here and watch the clock until. There we go. 8 o'clock. See, we have the benefit of having globally synchronized clocks, more or less. Good morning. Glad to see everybody here. So let's start with the usual thing. We'll talk about logistics. So project 1 grades for both code and reports are posted. Project 2 grades for code are posted. Project 2 reports are pending. So we're now working on those. Don't forget that project 3's on-time due date is in a couple of weeks, 2 weeks, I think. It's still January, so it's hard for me to think of February as being that close, but it's tomorrow. So, and of course, project 4 and 5 are out there as well. I did make minor updates to the project 3 base code repo. Most of them were just comments. There was one small set of suggestions for results, like 5 lines of code or 6 lines of code or something, pretty small. But somebody thought it was significant on Discord, so I was like, okay, fine. For the 14 people who decided to do something for the alternate path, project path, I see that you've submitted stuff. I haven't looked at it yet. Shocking, right? Deadline was midnight last night and I haven't already reviewed it. It doesn't look like anybody submitted something for the open source project, which I thought was strange because somebody yesterday was talking to me about it on Discord. But and they picked a really cool project to work on too, and they'd lined somebody up and everything. It was just like, wow, this is going to be great. I will have office hours this afternoon. That'll be on Zoom. You can post questions. You can show up on Zoom if you really want, but find that a lot of people are shy that way, and that's fine. So I'll record them, and you don't even have to be there. You just post a question on Piazza or pass it to me on Discord or something. I can answer it. There is one reading here. You don't have to read the whole thing, but you will see that the figures that I've used today in the lecture are based on this paper. This is fairly old, 2002. So, and it was a survey of failure recovery mechanisms, rollback style recovery mechanisms, which is what we're going to be talking about today. And then there was a cool little video I found. It wasn't very long. It's like 3 or 4 minutes on fault tolerant techniques that you might find interesting if you're more of a video kind of person. And then there's a nice blog post about microservices failure handling. So I've spent a lot of time up to this point emphasizing that we are concerned about failure. Well, what we're really concerned about is being able to survive some level of failure. And yet, we went through FLP. FLP said, given this particular model, and it's really important you keep in mind that it's a very general model. The mathematicians want to make broad, sweeping generalizations. They want to be able to say these things are strongly true, but unfortunately, we weren't able to say there's a strong model for dealing with even a single arbitrary failure. But I think that a lot of that ties up into the model. And what we're going to do in the real world is we're going to say, well, okay, so we can't do this in this very abstract, broad model, but we can do that so it's good enough for us in a finite real world. Anybody have any questions at this point? As long as it's not for financial advice or something. What's the next great cryptocurrency? That would imply there had been a previous great cryptocurrency. But actually, I have a friend who paid his undergraduate tuition bills mining cryptocurrency on the lab's computers. That was like 10 years ago now. And then for a while, he was doing a lot of trading, and I think he paid off the mortgage on his house in Texas, just trading Ethereum. Like, it's sort of scary. It's like buying lottery tickets. Yes. Is it true that chain replication sends fewer messages than other forms of replication? Chain replication does in fact decrease the number of messages, right? So if you go and you look, and the problem is when you make small pictures, it's not as obvious when you make a larger picture. So if you just simply do like replication, the base replication model, which is you have a primary and then you have multiple secondaries, what you're doing is you're sending messages between each one of them pairwise. When you send from the primary to a secondary and it sends to another secondary and it sends to another secondary, you actually do decrease the number of messages. Whether or not that's significant or not is a different matter, because realize what you've done is you've taken something you can potentially do in parallel. You can send all these messages out and then wait for all the replies to come back, versus now I'm doing it serially. So simply decreasing the number of messages may not necessarily mean that it's faster, but it may mean that it is more efficient in its use of the network facilities you have available to us. We don't worry too much about that these days, because literally you can actually go out and get network cards that are as fast as the bus that the network card uses to talk to the computer on. I mean, we've almost essentially turned our networks, no, we've turned our networks into just a reinvention of a multi-processor, multi-node architecture single computer. I mean, when we started out building big computers, what we did was we put fast buses to send messages between the various processors. Now we just simply use a network card to send fast messages across the network. It looks an awful lot like the same basic model. So networks are really, really, really fast these days. And so this is always what makes choosing a particular technique a little more difficult than you would think from just an abstract level. From an abstract level, you go, oh, great, you send less messages, it must be better. But from a concrete level, that really depends on what the cost of sending those messages are, if that makes sense. I gave a link to somebody for this. There's a paper called Cost, it's a 5-page workshop paper, and it's just this beautiful analysis that basically says we build these big distributed graph processing systems, which is one of the big uses for distributed systems at high scale. So you can have 1,000 nodes. I actually have a picture of somebody standing in a data center with a 70,000 node cluster. It's literally racks and racks and racks and racks of computers, and they're all talking to each other over a network, and it's acting as a distributed system. The kinds of problems you work on can be very large, and you can spread them out. But what's interesting about McSherry's Cost paper is he said, I can do the same thing that you're doing with your 100-node cluster on my MacBook. And he literally wrote code. It was very efficient code. He wrote code, I don't know if it was Go or Rust, I don't remember, but he wrote some code, and he demonstrated that those same workloads that they were running on these big multi-node clusters ran faster on his single machine. And a lot of that is because of the overhead associated with communication. He didn't send any messages. So it's faster because he didn't send any messages, but he was still sending messages, between the components on his machine. He just didn't send them across the network. So we end up with a lot of engineering choices in distributed systems. We end up doing things that are efficient for the problem we are trying to solve. But then we give you a different scenario in which the resources are different, And now you reach a different conclusion as to what's an optimal solution. Think of it as job security. You get to do the same thing over and over again and try it in different ways and figure out what works and what doesn't work. Any other questions? Let's start with a failure. January 25th, 2023. I mean, it's great. I don't have to look very hard to find these things. This one was a very interesting meltdown in this service called Azure, which is Microsoft's cloud service offering. And it affected, I don't know, pretty much everything. It knocked out email services. It knocked down their OneDrive, which is where they do data sharing. SharePoint, which is another data sharing solution. Why have one solution for a problem when you can have 6? And it goes back to that point I was making earlier, which is you create these solutions, they work in a particular scenario, and then they live on forever. But you go, oh, we could do this better next time. So we end up doing it better next time, but people still use the old one. It is the curse of technical debt. Anybody ever written any code? Have you ever gone back and looked at your code and gone, oh my gosh, this is a piece of shit? I mean, the most embarrassing thing to do in the whole world is that you pick up some random piece of code, you start looking at it and go, who wrote this piece of garbage? And then you look at it and you go, I did 15 years ago. And you're not quite there yet, but you'll get there. It happens. So these things live on. So Microsoft has this huge collection of services. They sell in various and sundry different ways. This was great. I love these failures because it's almost always somebody did something that they didn't know what it was going to actually do, and they shouldn't have done it in the first place. And this is another one of these. So what did? They had to change an address on a router. That's it. How hard could that possibly be? Well, okay, so, it started at 7 in the morning in the UK, and it ended around noon. So it was only 5 hours of outage. At the scale of something like Microsoft Azure, we literally are talking about this costing people millions and millions of dollars. And it touched everything. It touched government services, it touched individual small businesses, it touched large businesses, and there were some people clearly scrambling to fix it. These things happen. They happen all the time. So they did a wide area network reconfiguration event. Literally, if you read it, it basically says we had to change an IP address on something. And that means then we have to tell all of the other things we talk to, because these are routers, we have to tell everybody else what our new configuration is. And then everybody else jumps in and says, oh, I have to recompute my tree, because they're maintaining this very large routing graph. How do you get packets from point A to point B? Well, we actually know exactly what the right path is, because we can take the graphs that we have of the network and we can compute where it should go. Shortest path algorithms. One of the people I used to work with who graduated from UBC a long time ago did a lot of work in routing in the early days. It was very interesting because he did the IP multicast work. I think I've mentioned him before. And I learned a lot about routing, because at the time there were basically 2 different routing protocols, and eventually somebody was able to demonstrate they were actually the same thing. There's not really a lot of different ways of doing this, but it's complicated, because as the size of these things grows, they become fragile, in that even a small event can cause you to have to recompute routes through the entire network in order to route packets efficiently. And they handle a fair amount of change without you really noticing it. But for whatever reason, this one really walloped them, and that was unexpected. And then it affected other things. So everybody's sitting there recomputing and they're going, I'm going to stop delivering anything until I know what I should be doing. Network equipment doesn't have a lot of memory in it. Certainly not the kind of memory that's necessary to store even a few seconds, believe it or not, of packet traffic. I worked at a network company many years ago that did asynchronous transfer mode equipment. And in ATM, all the packets are 48 bytes long. And they literally start computing. And they do this, and it's not an unusual technique. It's a very common technique. They literally start sending the packet that they have received before they finish receiving it. What they call cut through. It's a very efficient mechanism for getting packets from one node to another node. Because we can't afford to store them. Because what we've learned is, oh, we'll just add memory to our network device. And we've learned it doesn't work. No matter how much memory you have, queuing theory basically beats you over the head and says, guess what? You're never going to have enough. So not forwarding packets, really bad. I loved the comment. This change command had not been vetted. Oops. This is a very common theme in these failures. We did something that we didn't know what it would do. We're going to have failures where we did something we thought we knew what it was going to do, and it did something different. But this is very common. Okay, so it didn't take that long, just over an hour for things to mostly recover. I loved that part. Nearly all network devices had recovered. We had the last of the networking equipment out by 9:35, so 2 hours into this event. But unfortunately then, we had something else that mitigated against this and turned itself off. So we experienced increased packet loss. Even though the network is now stabilized, we're still seeing packet loss. This is why I say, no matter how much memory you put in there, it just never, it takes time. And in this case, it took someone manually rebooting network equipment to get it to go away. The moment you see that something had to be done manually, you know it was bad. In distributed systems, especially at the scale of Azure, nothing is done manually. Everything is automated because automation increases the speed at which you can do it, and it decreases the likelihood you're going to screw it up. I mean, it's like me trying to put this stuff for this class together, and I'm typing the same information in different places. I can't get it to converge eventually, but it takes time. Manual processes does take a lot of time. I mean, I've definitely found that in a lot of the work that I do is that I'll write a Python script to do something rather than do it manually because the Python script will do it in a form that's automated and consistent. So I love the corrective actions. They said, we blocked the highly impactful command from ever running ever again. You will never run this again. They're very polite. This was in, this is on a on a Great Britain blog, but so they're, of course, more polite than Americans. That's not a high bar. And then they require, they're going to add some guidelines for command execution in general. In other words, we're not going to make this mistake again. It happens. This is a big, big company. I'm sure a few of you have heard of Microsoft. They even have offices here in Vancouver. And there was a link to the actual blog post. So let's talk about what our goals are today. What do we want to get out of today? I've been talking about failure. Now let's start talking about how we deal with failure. So you may be under the impression that failure is something to be avoided. I don't want to fail this class. I don't want to fail any classes. But the reality is that the world in which we actually implement systems is filled with failures. It's filled with things not behaving the way we expect them to behave. not doing what we want them to do. Disk drives fail. Networks get unplugged. IP addresses on routers get changed. What are we going to do? How are we going to deal with this? Well, when your computer starts doing wonky things, what do? You sit there and stare at it, waiting for it to get better. Oh, please get better, please. You guys are afraid of failing and answering the wrong thing. Say something! Right! I have a t-shirt for that I haven't worn yet, but yes. It says if I'm ever on life support, unplug me and then plug me back in and see if that fixes things. Because that's exactly the kind of failure recovery model we're going to be talking about today. We can disguise it, we can make it pretty, and we can talk about it being checkpoint rollback and all that, but bottom line is we reboot and go back to a known good configuration. And that's why we reboot. And I plugged in the laptop this morning, and of course Discord was sitting there spinning and wouldn't connect. And so I had to kill it. And of course these things now live in the background because they want to always be on. And so going and killing Discord was more than just simply exiting the visible part of the program. And why did I kill it? Because I didn't need to reboot the whole computer. I just needed to restart Discord. I just needed to restart that one broken application. So there's this interesting tension between, oh, we want this stuff to always be available, and the way that we're going to deal with failures is, of course, to just simply restart something. So let's talk about this in more detail. Not only do we need to be able to get back to so when we reboot, we get back to a known good configuration, hopefully known good configuration, unless things really melted down, like the disk drive itself is corrupted. Been there, done that. At that point, then usually you take the storage device out and you replace it. But let's talk about how we do this in a distributed system. Let's talk about how we're going to do this in our systems. So something goes wrong. It is a fault. That fault gets noticed. This is what I find fascinating. I've done so much debugging over my career. I've actually seen cases where I find a bug and I go, this bug has been around for 15 years and nobody's ever noticed it before. How could this be? It flipped a single bit. One bit. Nobody ever looked at that bit after it got flipped. Or they looked at it so infrequently that it wasn't possible for us to figure out what the bug was. I see this happen. It happens a lot. So if a fault occurs and no one notices, it doesn't matter. And that's one of the fascinating things about this, is you think like we've got all this memory on our computers, but most of the time, even if you scribble over some of it, nobody notices because they never use the results in that location. Things go wrong. Nobody notices, you move on. It's kind of like being a little kid. You know, you do something wrong, nobody notices it. It didn't happen. This is why you end up in a denial behavior. All right, who took the cookie? Not me. When someone notices it, though, now it becomes an error, because now what's happening is they're relying on information that is no longer correct because there was a fault. Something went wrong. When you're writing a program and an error occurs, what do? You either deal with the error, which is kind of what we're going to be talking a lot about here, or you go, I don't know, something went wrong, and you tell somebody else. And you propagate the error. And now at this point, this is actually an official failure. Okay, so now we have kind of a model for what we're talking about in terms of failure. Somebody has to notice it, and it has to get reported. How are we going to deal with this failure? We have different kinds of failures. We have, and I've talked about them, the transient failures, where things work and they stop working and they start working again because, you know, I unplugged the network switch. because I needed to plug in the vacuum cleaner. There's all these stories about like data centers where some company with a small data center, like a closet with stuff in it, that where their server reboots every Saturday at 6 p.m. and they don't know why. And then they come in and find out that the cleaning lady has been plugging the vacuum in there and unplugging the computer because it's only one outlet. Stuff like that. So they're transient. They happen with some periodicity or without it. If you have a periodicity, then you can actually study that and say what's happening, what else is happening around it at the same time. If it's just a totally transient failure and you don't see a particular pattern, those are actually harder to diagnose. This is when your computer is doing wonky things and you start replacing pieces of it. I mean, you don't really do that on laptops these days, but if you have a larger system with components in it, you can switch the components out. And that's the way we fix computers. Well, that or just throw it away and buy a new one, which is, I suppose, a replacement model. It just happens to be a total replacement model. Anybody ever had a computer break on them? Was that because you threw it at someone? Same diff. That's the convenient cover story. I dropped it right on that person's head. A transient failure might only happen once, or might only happen very, very so seldom that we don't actually notice a pattern, versus where it's intermittent, where it's happening more than once, and we start to notice that there's a pattern to it. Well, let's see, a couple times a day, the computer spontaneously reboots. A permanent failure is one where, I'm sorry, your laptop was in a house fire and it's never going to work again, ever. It's done. It's finished. So we have kind of different scopes for these things. A fail stop is where it just crashes. It just stops. We can have things that are timing related. These are very interesting problems, and we end up solving these in distributed systems using the techniques I'm going to be talking about today. And we've been using these kinds of approaches to things for decades, and they are very heavily used in distributed systems and even some single non-distributed systems. Something just doesn't get done. The omission. Why didn't that email go through? I don't know. What happened to it? Was it on his laptop on its way to somebody else and he dropped it and never got through? We don't know. So there's lots of different ways for these things to manifest. And Byzantine is just where, I don't know why. I stole the picture, so I'm not sure why they decided to use somebody on a horse. Byzantine Empire. Does anybody know why we use the word Byzantine? So this was an empire where basically people lied a lot, and it was kind of a cultural aspect. And so we talk about Byzantine failure as being misinformation. Now, in fact, the reality is that all wars are basically based on misinformation, propaganda, misinformation. We tell people what we want them to hear, not what they actually, well, not what is even a truth that we know. Disk drives lie. I saw this very interesting talk many years ago by a gentleman named Jim Gray, who at the time was working for Microsoft Research down in the San Francisco Bay Area. He went on, after that talk, obviously, he went for a day sale and never came back. So to this day, we don't actually know what happened to him. And he is the person who is credited with creating two-phase commit. He was talking about disk drives and the fact that they had 3 teams at Microsoft at the time, quite a number of years ago, that were heavily invested in protecting and in storing data on disk drives. There was the SQL Server team. SQL Server is a database. There was the Exchange team. Exchange is a mail server. And there was the NTFS team, and NTFS is a file system they use on Windows. And of the 3 teams, one of them was doing end-to-end checksums on the data. That was the Exchange team. And they actually were finding that sometimes they would read data off of the drives, and it would be wrong. it wouldn't actually pass their checksum. But the SQL Server people and the NTFS people weren't doing that. And they were like, well, okay. And so they went back and they started doing experiments, and they found that indeed, disk drives lied. Sometimes disk drives return data that they say, this is the correct data, because the disk drives have their own checksums going on here too to make sure they don't return to you bogus data. But this is the data, and it's not the data. Wow. So that's a Byzantine failure. And that's what's insidious about it. You can think that the person or the entity that you're using, you're relying on, is doing their checks, and it doesn't actually work right. A bad disk controller can cause that. A disk controller that corrupts the data and then gives it to the disk drive will take it, add its checksums, put it onto the media, and then when it reads it back, the checksum is fine, but the data was corrupted in between the application and the disk drive. How do we deal with failures? So, of course, the best thing to do is just simply don't fail. Like the whole thing I said, if you don't want to have to use the debugger, don't put bugs in your code in the first place. Sounds like a great idea in theory, and in practice, it turns out it's not very easy. My recommendation is, if you don't want to have bugs in your code, go into management, or better yet, marketing. Because they don't have any bugs in their code because they don't write code. And then you can be laughing at the software engineers, the ones with jobs. I don't know if anybody noticed the t-shirt today, but it's the programmer with a job, programmer without a job, and one of them is an individual disheveled. That's the one with the job. The one without is wearing a suit. And you wear the suit because then you look like you're in marketing. I used to do that. I'd go to standards meetings wearing a suit so people would think that I didn't know what I was talking about. A very effective disguise. They just assume that those ties that you put on are in fact cutting off the blood supply to your brain. In fact, one of the things that I want to talk about, I haven't actually written that lecture and I don't have a set of notes to crib off of yet, but I think I'm going to do it a little bit later, is how we can actually do avoidance in a formal way. There are mechanisms for formal verification that are actually quite useful when we build distributed systems. The problem with formal verification techniques is they tend to be very difficult to implement in large systems. But there are some ways we can get many of the benefits of formal verification without experiencing the state space explosion that it usually has to deal with. I mean, essentially, when I give you a state space that's larger than the known universe and you have to search it, you're never going to get there. This isn't going to happen. When we can, a great way of dealing with this is to roll things back. It's not always possible, but in many cases it actually is. We can actually say, well, that stuff you were working on for the last 24 hours, sorry, it's gone, but at least you got what was there 24 hours ago. It's like if your computer crashes and you have to go use a backup copy of some file that you were working on at the time. It may or may not have made it to the drive, but odds are, because we build our systems to be fairly resilient, there will be some version of it. We can detect a communications failure by using a heartbeat. Not uncommon. We can use error correcting codes. I was talking about checksums. Checksums are one of the simplest of error correcting codes. I don't think anybody's taken 421, but when Nick Harvey teaches it, he puts in information theory. Claude Shannon's work from the 50s. Very interesting stuff. It is the basis of how we do compression, for example. We start looking, and when we start to see patterns, we realize that we can actually more effectively encode the same amount of information with fewer symbols. Kind of a very high-level, hand-wavy sort of explanation. Error correcting codes are another way of thinking of that. When we're not entirely sure about the data, we can add some extra stuff to it and then we can figure out what the data should have been, most of the computers in this room have parity memory. Parity memory will detect a single error in another memory cell. If you want to go spend the money, and we do this in servers, you can actually get what's called error correcting memory, where we can use 2 bits of extra information for every byte. That's 25% overhead, right? Pretty significant. We use 2 bits of information, and we can correct a single bit error. So we can figure out which bit is wrong and fix it. Well, it turns out that generalizes. We actually use multi-bit error correction codes for scenarios where we know that there is a high probability that at least one of the bits will get corrupted. So in fact, what we do is we can say there's a high probability that n bits will get corrupted, so we need this many additional bits in order to be able to recover from that class of failure. So we're going to have cases where we actually have to do some sort of recovery, where we can't actually just paper over the fault. We're going to have to do something to recover from it. And that's going to be like our rollback. We're going back to a previous state or even a different copy, fault tolerance. So we're going to talk about rollback recovery, because that is a very common technique for us to use. Has anyone ever heard of a transaction? So the fundamental idea of a transaction is that we have a series of discrete steps that we take, but we only want either the beginning or the end of that series of discrete states to be visible. Remember, if you don't see it, it didn't happen, right? We're going to exploit this now in the other direction, which is we're going to allow ourselves to recover by doing a series of things that might fail and keeping enough state around that we can handle either outcome. Either we get all the way to the end and we make it succeed, or we roll back to where we started and it's as if it never happened. That's rollback. That's what a transaction does. It implements rollback. The most common way of doing this in a transactional system is through a journal or a log. Same diff, different word. So when we roll back, we go to a consistent state prior to the failure. Now, here's the thing that I have learned pragmatically, and that is it is really easy to write rollback systems, and it's really hard to identify consistent states. Because consistency is almost never defined by the level at which you do the logging, by the level at which you do the rollback. Something above you is defining what their consistent state is. And if they get their transactions right, so I build a nice log, you start a transaction, you do a series of operations, you end the transaction. It's on you to make sure that if that rolls back, it goes to a consistent state. And it turns out that defining consistent states is harder than you thought. Remember that consistent cut thing, and we were talking about that? The reason this is important is that when we can make consistent cuts, we can reason about them, and thus we can argue that they are consistent states. Or maybe a different way of thinking of that is it has to be a consistent cut in a distributed system in order for it to be a consistent state. The reverse isn't necessarily true. In other words, not all consistent cuts are going to be consistent states, but at least we can reason about them. So a very common technique here then is to do something, and if it goes wrong, you go back to where we started and you try it again, and you see if you can get it to happen again. Checkpoint rollback. So remember, we had our consistent cuts, and those are going to be where we're going to start. This is exactly the same model. What that means is we can't have things that are visible here. That right? Sent the message here, we received it there. Oh, that is consistent, right? This is the inconsistent one. We can't have messages that are visible here that weren't visible there. That was the inconsistent cut. So this is our model of consistency right now. How do we capture that state? Well, we can go back. We'll go back to a previous cut, and we'll go back to a previous cut. We'll go back to a previous cut. We'll go back to a previous cut until we find one that's actually consistent. And this is a model for rollback. Of course, how far back do you have to roll? Were we consistent at the very beginning of the system? That's why we reboot, honestly. We reboot because that's what it does. It takes us back to a known consistent state, which is the state at which we started. And our hope is that when we reboot, we're going back to that exact same state. And then we try it again. Well, unbounded rollback causes some problems for us because that means that what we might actually do, and I mean this happens with my laptop, if it gets screwed up too badly, I do a full reset. It's like a complete clean reinstall of the operating system. There's a consistent state for you. The problem with that, you've lost all of that work in between. So that's why we probably don't want to do arbitrary rollback. So what we can do is we can make periodic statements that say, here, this is a consistent state. You don't have to roll back before this state. That now becomes a checkpoint. That's it. This is, we know, or we're vouching for, I might be lying, I might be wrong. In which case, I'll reinstall everything and start all over. Here's a consistent state. You don't have to store the information about what happened before this point. And we talked about that when we were talking about how we progress through consistent cuts as well, about how we store the messages. But we only stored the messages that happened after we took our snapshot. We can discard the ones before. So we actually don't need an infinite amount of memory to do this. We need a finite amount of memory to do this. A lot of this is going to involve, and I was talking about different levels of the transactional consistency. A lot of this is going to involve what the granularity of the transactions are. I just gave you the high-level transactional granularity you deal with, which is, sorry, machine hosed, reset it. Back to factory reset. Here you go. It's just like it came from the factory, and the factory said it was working. That's a very, very high-level transaction. We probably prefer not to do that because it's a very high overhead. How many people have reinstalled their OS on their computer before? Well, the rest of you are living like amazing existences. And don't worry, eventually you will. What we do is we try to break things up into smaller chunks, smaller units. We're going to call those transactions. In a transactional system, what we do is we actually say, I'm going to start a series of operations that need to be done atomically. Here's operation 1, here's operation 2, here's operation 3, here's operation 4. I'm back in a consistent state, so I'm going to end the transaction. There's no guarantee of consistency if only some of the messages in the middle, some of those operations get performed. So that's why when we do rollback, we go back to the previous consistent state. We undo all those transient intermediate states because we can't guarantee the consistency around those. Some applications, very few, but some, actually will implement this kind of consistency guarantee themselves. They'll have their own journal. They will provide their own transactional guarantees. When you use a database, that's one of the key functions of a database. It provides these kinds of consistency guarantees. When you're sitting there using a word processor, your consistency guarantees are pretty coarse. If the word processor crashes in the middle of you editing the document, maybe it did the convenient thing and saved a version of it. Anybody ever used a word processor before? You guys don't like to answer any questions at all. It's like, this is an interrogation, stop it! I'm a file systems person. I've been a file systems person for a very long time, and I can tell you that all the word processors in the world, even the dumbest ones, do exactly the same thing, and that is when you edit a document, they load it into memory, you edit the document, and then they save it to a new file, and they rename the old one, and they rename the new one. And do you know why? It gives them a consistency point. It gives them the ability to say, you can recover by pulling the old version. Because I renamed the old version. The new one is being written to some transient name thing that will probably go away if the computer reboots. But the old version, still there, so you can get back. That's their consistency model. This is a very coarse consistency model, but it's sufficient, and it's one that the underlying system guarantees. But I did file systems. One of my jobs as a file systems provider is to actually do some of these things atomically, like rename. Rename is kind of the sticking point in a file system, where if you don't do rename properly, you can end up with 0 pointers from directories to the file, or 2. 2 is better than 0. But what you really want is 1, normally. That's why we ended up adding journaling, because it was the only way we could guarantee that kind of consistency. It's a lot of work to add that one little guarantee. But this is what happens, is that we have different layers of guarantees, and different services will then use the guarantees of the lower layers to build their own level of guarantees. And, well, we'll give you back the last version that we saved is good enough for a word processor. Trying to do something that is more transactional than that would be a lot of extra effort for them. So they don't do it. So let's talk about some basic rollback mechanisms. We have checkpointing. Very simple snapshot. We can have uncoordinated checkpoints, which aren't very satisfying, but you can do it. It doesn't require any coordination, which is why people like to do it that way. We can coordinate our checkpoints. So we have multiple different processes, and they need to coordinate what's going on. So we have a more globally consistent checkpoint. So think of these as uncoordinated means we get a locally consistent one, but it may not be consistent with anybody else's state. When we coordinate, now we get a globally consistent one. And since we already have modeled our distributed system as processes with messages, we're going to look at how we can use that model to do communications-based checkpointing. Then we're going to go to a different technique, which is called logging, which has been around for a very long time. It tries to eliminate some of the problems with checkpointing. And of course, then I'm going to wrap up by talking about which one do you actually want to use. So checkpointing, you save some sort of state, that is the checkpoint. That needs to be written onto some sort of durable storage. I mean, I don't know why, but I just used a disk as an example because the diagram that I was using used a disk. We use the term disk very loosely these days. A lot of times it's just a piece of non-volatile memory of some sort. Actually, it's very interesting. The old model for computers was they didn't really view anything different between computer memory and storage. They just viewed it as a continuum. So memory was faster than disk, but it was all just memory. IBM actually still builds machines that are called single instance stores, and that's exactly what they do. It's like a tiered memory system where you have a fast tier and a not so fast tier and a really slow tier and then the glacially slow tier. But it's all one address space. It works. It's an interesting way of thinking about things too, because in fact the way we actually build computers is already tiered. Your computer has some super fast, 500 picosecond memory in it. Very small, very expensive. Most of the work is done in that 500 picosecond memory. Then it has some memory that's a little slower than that. It's about 7 nanoseconds. So it's 14 times slower. And these numbers are approximate, right? Obviously, it's going to vary depending on the architecture, but the ratios haven't really changed much. We haven't made processor memory much faster. Have like propagation of electrons through media limit us. And then we have another layer of memory, and that one is about 35 nanoseconds. And then we have another layer of memory, and that one's usually about 70 nanoseconds. And 70 nanoseconds is about the speed of DRAM. And it's really, really interesting to see what happens when you don't have those little tiny memories that are really, really fast in front. Suddenly the computer becomes unusable. So this is not unusual. At any rate, we store it someplace where we know that it's going to be there when we need it. Something non-volatile is the idea. So the benefit of a checkpoint is that this is now quick restart, right? So if I've got my tiered storage system, I wrote this stuff out to my cold tier, I have to reboot the machine, or I have to roll backwards, I can just go grab the copy that I saved, and life goes on. There's a lot of overhead associated with writing one of these checkpoints because I'm moving data. And the bigger my working set is, the more data I have to actually move. If I have a machine with 3 terabytes of memory on it, and I need to move 3 terabytes, because that's the size of my snapshot, how long will it take me? Current DRAM speeds, so the fastest bus in the computer, are around 40, 50, 60 gigabytes a second. 20, 30 seconds. Do you think that's practical? Do you really want to wait every time your machine takes a snapshot for 30 seconds? Can't do anything else while that's happening. That's not very practical. That's the problem with checkpoints. They have a lot of I/O overhead. And I just gave you the fastest example I could come up with. I literally was working on a machine that had non-volatile memory directly on the memory bus. And you start doing these computations and you begin to realize that the cost of moving that data is far too high for you to ever actually move the data across there in a asynchronous fashion. Okay, so that is a problem. Small projects, checkpoints, not an issue. If you're doing 64K or even a megabyte, maybe even a gigabyte these days, okay, I can tolerate that. I can tolerate 100 nanosecond or 100 millisecond delay. Because 100 milliseconds is below what humans can generally observe. When it gets above 250 milliseconds, that's when you start to notice it. That's when, like, calls. Oh, I'm bouncing off the moon. It takes 2 seconds. So I notice the delay on that. Logging, on the other hand, is this observation that, you know what? Those things don't change. So why are we actually preserving all of the data when we could just preserve just the data that changed? So here we go. We can log what data was there before we made the change. That's an undo log or rollback log. We can record all of the values we're going to change before we actually change them. That's a redo log. When I implemented the log years and years ago for the file system we did, I talked to people who knew about this stuff, and they said the feedback I got was, actually, there are benefits to having both. And so this was my contribution to the slides as I'm building these things. Great. No, wait, there are reasons. There are times you actually want to do this, and that's because it loosens some of the ordering constraints that we will see otherwise. You see, in a redo log, you have to record all of the steps you're going to take before you can commit the transaction. In an undo log, you have to write those records that show how to undo things before you change the data. Otherwise, you can't roll back. You can't get back to where you were. If you have both of these values, you actually have some flexibility about when you have to wait for things to happen. So what is the benefit here? Way smaller than checkpoints. Almost always the working set of actual changed data is much, much smaller than the total size. When I got a terabyte of data, I'm not changing a terabyte of data every second. I can't even write it to memory that fast. So logs are very efficient. They're very effective at keeping track of these changes and allowing us to roll back to a previous known good state. But recovery does take time. And depending on the kind of log you use, you may have to actually search through the log to see if there are other operations that are causally dependent on this. In which case, then you have to search through these. So let's look, the figure is actually from that paper, 2002 paper. So let's look at sort of examples of that. So we start at a time where we say we're consistent, right here, the recovery line. As time goes on, and we get messages passing between the processes and things happening and coming back and whatnot, and then a failure occurs all the way here on the far right in process 2, that's the point at which we'd be doing our recovery. What do we go back to? Well, we can always go back to the starting point. That's a super easy way of doing it. We could take checkpoints and roll back to the last checkpoint, but of course now we have to worry about getting consistent checkpoints. Do we want one that's globally consistent? Are we okay with just having locally consistent ones? We can have logs. The benefit of a log is that we can combine logs with checkpoints and say, periodically, we're going to take an entire copy of the state of the machine, and then we're going to log the things that we do from that point forward. And so if we have to roll backwards, we can go back to that checkpoint, or we can go to something intermediate. This is not an uncommon technique. If you know how video is actually compressed, video is compressed by incremental changes. So we have what's called a reference frame or an iframe, and then we have the changes from the previous frame, and then the changes from the previous frame. Turns out those change frames are way smaller. The delta frames are way smaller than the actual main frame. But the reason we do the main frame is because eventually the cost of recovering the current frame becomes more expensive than just building another checkpoint, another frame. So I store the checkpoint, and now I store a little one, and a little one, and a little one, and a little one, and a little one. And now if I want to reconstruct things, I have to go back to the checkpoint, and then I have to go and I have to replay them. Okay, so now you can see why there's a balancing point here where you pick a time or a size or some criteria for picking your checkpoint and then logging after that, and then doing another checkpoint. This gives us fast recovery, because the worst case, we just go back to the previous checkpoint and then we roll things forward from it. And it keeps the log relatively small. But we need a consistent cut to be able to do this. Because now we have to be able to, if all we're going to do is just checkpoints, then there's no reason to keep that log around. We'll just use checkpoints. So the benefit of the log is it's going to allow us to get to some point in recovery that we know we're consistent. Question in the back of the room. So what he has just said is, so these things are serializable. Yes, you're right. In fact, the log defines an ordering of potentially unordered events. Because remember, that was one of the things that made reasoning about the systems earlier hard, was because we didn't even really know the exact ordering of those events. And in essence, the same technique we used before to get us to an ordering. Because remember, the conclusion was, okay, maybe the ordering we end up with isn't exactly the ordering it really happened from that mythical global perspective, but it's close enough. It's isomorphic, and that's all we need. But you're absolutely right. That log defines an ordering of the events. Now, the interesting question is going to be, do we have a global log or do we have lots of local logs? And most of the time what we end up with are lots of local logs, because a global log essentially then does this kind of ordering of events across the whole system. That's fine, but now you're going to be waiting a lot because you're going to all be synchronizing to what turns out to be kind of a crappy implementation of a global clock. Might as well just simply implement Spanner and buy yourself a CPSC clock. So how are we going to do checkpointing? Let's start with uncoordinated. That's me, clumsy. No ordering between the checkpoints. Oh, yeah, right. That's right. Okay, so before we get there, let's talk about what our model for the system is. We have a fixed number of processes. That just simplifies things. We'll get to a point where we can relax that, but we're not there yet. Let's keep it simple. We have a fixed number of processes. We only communicate via messages. So this fits very well into the model that we were using earlier in the class, and we interact with external actors. I think that mentally, I think of these as the client. These are my clients. My internal state and my internal inconsistency is what I'm trying to mask from these external actors. So in fact, consistent points are the only points I allow these clients to see. So they can't see data that is inconsistent in my system. I only show them things that are consistent. And thus they only have consistent views. And that is really why we build distributed systems. Because now we can take application programmers and we can give them APIs with consistent views of data that is potentially inconsistent under the covers, and they don't have to worry their heads about it. I'm a systems person. I know that applications programmers are simple, loving people, but they write crappy code. And you want to make it as easy as possible. You laugh, but we've now got AI agents that they're trying to train to write code, and they're doing a pretty good job of it. It's sort of scary. And they suggest code. I'm like, really? I'm sitting there in VS Code now, and I'm like writing a paper, and it's suggesting text that I want to use. Like, well, sometimes it's right, but sometimes it's wrong. But that's the world we live in. Less and less actual code writers. So these guarantees that we provide are very important because they actually do simplify application development. Those clients are easier to reason about because they don't have to worry about this kind of asynchronous amorphism, lack of ordering, gosh, things could go wrong kind of model. We give them a bounded set of guarantees. Eventually, we could say, sorry, your data center melted down, and we don't have a recovery model for that. Bye-bye. But that's just being practical. Otherwise, we end up back in the FLP world where we go, sorry, can't even handle a single fault. Everything's got to work absolutely perfectly. That doesn't reflect the real world. We can't do that. No network partitions in this model. We're going to keep it simple. We will reason about network partitions later, but we're not going to go there yet. There are things that you can vary in this model. The messages can be in order or not in order. That's fine. The communications can be reliable or not reliable, and you can design things to tolerate a certain number of failures. We know there's a number of failures we just can't tolerate. If everything fails, we're done. So in an uncoordinated checkpoint model, all we really do is have each process maintain its own checkpoints. And then when it comes time to recover, what we do is we actually have to look at all the checkpoints and say, can we come up with a consistent cut? Because if we can come up with a consistent cut out of all of those checkpoints, then by golly, we got ourselves a solution. And ideally, we take the last consistent cut. Because if we take an earlier consistent cut, then we are throwing away state. We're throwing away stuff that we did that maybe somebody wanted. Maybe you can see why that's not a very good model if you're trying to provide services to an external client. Well, we might have rolled back to last Tuesday. But maybe that's good enough for the particular usage model. Amazon's S3 service, which is an object store, has very strange semantics when you rewrite objects. You literally can read it, and you don't even know where it's coming from. Right? You just get an API, you read the object, and it gives you back some version of the object. And it can roll backwards, and it can roll forwards, because there are different copies of the object, and it just depends on which one you get. So what you learn is, if you want consistency guarantees in that model, you never overwrite an object. You write an object once, and you never overwrite it. And therefore, you either get, sorry, I don't have that object, or here's a copy of that object, and then you know that it's the correct copy. And now you have a recovery model. How far do we roll back? Because if we could never actually find a consistent cut, we may actually have to roll back all the way to the beginning. Reboot, restart, reinstall. Not a very effective thing for me to put my distributed database on. Well, yeah, you just have to redo all your transactions since, December 31st, 1969 at 5:01 p.m., which happens to be the beginning of Unix time, January 1st, 1970, UTC. You have to remember these kinds of useless and meaningless pieces of information because it turns out that being able to look at a number and go, that's a Unix timestamp, is actually useful in debugging, as sad as that is. Uncoordinated checkpoints have some problems with them. You can have a domino effect where you lose everything. You do end up with lots of checkpoints per process, which is fine. There's no problem with that. But that's a lot of state to be storing around. Garbage collection ends up being a big issue here. Where do I reclaim that space that I've been using to store those checkpoints? When is it safe for me to do that? You can end up with lots of checkpoints that you can't actually get a globally consistent cut from, and therefore, what good was it? So it's easy to implement, but it's not as useful as we'd like. If we coordinate our checkpoints, then what we can do is, this is more like what we saw when we were talking about taking consistent cuts in our network before. Same thing. Now we're just actually applying it to our recovery model, which is, I have somebody who initiates it. Remember they send a marker message out? Right, okay. So these consistent cuts are going to be helpful for us for reasoning about globally consistent state here when we don't have a global observer. So this coordinates across all the processes by sending out those marker messages, and eventually the state all comes back, and now we know what the state of the system was. We know we have a consistent cut. We're done. We know the set of checkpoints that form a consistent cut. And therefore, that makes it easier for us to do things like garbage collection. I don't need to keep those old checkpoints. It's mostly distributed. We don't actually coordinate our checkpoints. We're just using the checkpoints as we observe them in the system. We find that consistent cut, and that gets us enough for us to be able to reason about when we do our recovery. Coordinated checkpoints, though, suffer from the same problem that we were talking about before when we were talking about distributed systems, when we were talking about messages and no global clock. That's the whole clock discussion back to haunt us. Are the messages reliable? Do we have time-bounded delivery? We know if we don't have time-bounded delivery, we're done. FLP says, sorry, can't solve that particular problem. It's too general. So we're going to have to time-bound it. And then, of course, there's that efficiency question, which is, okay, so what could I do to eliminate checkpoints here? I mean, it's not hard to sit here and think, maybe I only do the checkpoints when I get the marker messages. Could I make that work? Maybe. How do you coordinate the checkpoints? The simplest way, and one that's one of the oldest in the book, is we block and wait. Two-phase commit. The initiator starts the checkpoint. Non-initiators wait, block any additional work. They wait for a notification. Did this transaction commit or abort? And that's simple, super simple. There are variations on that that are a little bit more flexible than that, but that's basically it. And then there are all these other consensus algorithms. There are several other consensus algorithms that we will be discussing as we get further into the class, like Paxos and view stamp replication / Raft and blockchain. All of those are consensus algorithms. They all specify a mechanism by which we can take a coordinated checkpoint. They're just different ways of achieving the same goal, and they have different strengths and weaknesses. In a non-blocking system, we're doing this global checkpoint, global snapshot algorithm, where we need to find a consistent cut. I mean, we like non-blocking because now it means that we're not stalling things. And that's ultimately what we're going to want to do. And we're going to see that some of those more sophisticated consensus algorithms are popular because they mix blocking and non-blocking to try and achieve efficient implementation and still solve the problem. So one of the things you can actually do is instead of using marker messages, you can actually just piggyback on top of existing messages. So for instance, maybe you have a bit in the message that says this is also a marker. So you send a marker at the same time you send another message. So you can decrease your network traffic. That's just an optimization. It's not critical. You can do it. You don't have to have these in order. So the messages can get reordered. That's fine. Works, not a problem. The nodes themselves are operating independently of each other, so they get to make their own decisions, and they don't actually even need to be in communications with other nodes. One of the questions that came up was about what happens if I only have an outbound channel. I send out information. The temperature is. I don't care what the state of the system. I don't care at all, and that's fine. That works just fine here. You can use messages then to trigger snapshots. You can also use messages to force the checkpoint, the decision to do a checkpoint, or is this a consistent checkpoint? You don't actually have any state that you need to store. You don't need a checkpoint. That's the interesting thing about that. It's like it's the trivial case. You're like, yeah, I don't care. I mean, when your clock needs to be rebooted, you just reboot it, unplug it, plug it back in, and it continues, and it figures out what time it is and starts sending the timeout again. So yeah, it's interesting. You can have actors in the system that send messages but don't receive messages, and therefore it actually doesn't matter. You don't actually care what that is in a consistent cut because their state will always be reflected in the state of anyone they talk to where it mattered. The benefits of logging are, oops, that should have been compute versus I/O, not computer. Compute versus I/O. So logging uses a lot less I/O, but uses more compute because now I'm building these records and I'm checksumming things and I'm doing these extra steps that I don't have to do when I do a checkpoint. Generally, the compute is the win case. I'd rather use more compute and less I/O. I/O is slower than compute. A pessimistic log logs everything and allows your events to propagate out through the system. An optimistic log just keeps track of things that need to be undone, and you only write to the log as it's absolutely necessary. There's a synchronous versus asynchronous dichotomy here. One of the things that I've seen is that most people end up doing new value logs, which have to be written synchronously because you can't record the changes until the log information necessary to reconstruct those changes is persistent. Whereas in the undo case, you can record the changes immediately, you just can't make them visible, right? So that you can't present something to a client as being durable, as actually having happened when you're still in this intermediate state. But that gives you a window in which you can be very aggressive about initiating your I/O and then only block the clients coming in when there's a dependency where the I/O hasn't finished, if that makes sense. It's just an ordering frame. One of the challenges here is that since we have multiple logs and we have multiple messages in different processes, there can be causality ordering issues here. The reason that we like consistent cuts is that they capture causality. That's why we can't have an event's receipt in our consistent cut when we didn't see the send, because now what we have is we have one node snapshot that is before that message was sent and one node snapshot that is after that message was received, and those aren't consistent. That means I'm seeing a result where I didn't see the initiation of it. Which consistency mechanism should you actually use? Well, let's see. It's the diaper answer. It depends. What are you trying to accomplish? What is your primary objective here? What are your resource constraints? then it becomes an engineering decision and not so much a theoretical model decision. The reality is you're probably going to use some combination of these things. The editor example I just gave you is really a checkpoint example. They do checkpointing. You save an entire copy of the document and you create a new copy of the document and then you replace the old copy with the new copy. Done. That's a checkpoint in a nutshell. As the documents get larger, let's say they're a terabyte in size because it's a database and you've got a terabyte of data in it. Look, I have my 1 billion node graph database in it. And of course, you sit there and go, oh, nobody has a 1 million node graph database, except, of course, what is Meta? It used to be called Facebook, but when you become evil, you change your name. So you're no longer Anakin Skywalker, you're Darth Vader instead. Well, so now they're Meta. At any rate, how many people are there on the planet? This is a big, like in the news kind of thing, actually. We know statistically the 8 billionth person to be born simultaneously was sometime last fall, like November. There's 8 billion people. So there could be 8 billion nodes in Meta's database. That's not even unrealistic to think about that. That's a big database. Well, I don't want to checkpoint that. That's the point. I don't want to checkpoint that. Even though there's lots of changes to it, I don't want to checkpoint it. I'm going to be using a log. If I checkpointed that once a year, I'd be surprised. In fact, what I'm probably going to use is georeplication, which you could argue is sort of a form of checkpointing, but it's going to use logs to do that. Never thought of it that way, but that's true. If I take the log and distribute it to other nodes, so everybody starts with the same copy of the same database, and then I start making changes, and then I send my logs to the other nodes, and they replay their logs, then they have essentially created a checkpoint. We've just done it in a more efficient way. We didn't send the whole copy, we sent a copy of the things that changed. So I'm not going to go through this chart because there's lots of detail in there, and I don't think it's important in the high level understanding perspective. When you're sitting there trying to decide, how do I want to do my recovery, you're going to be picking one of these or multiples of these and combining them. Has anything changed since 2002? Well, networks are faster and more reliable, and storage is faster and cheaper. So that means that a system that you wrote in 2002, you might not build today because the cost-benefit analysis is going to be different. So what did we talk about? We just talked about fault tolerance. How do we deal with things going wrong? We know that things are going to fail. We know that we're going to have to deal with it. How are we going to deal with it? How are we going to get ourselves back to working as quickly as possible? Sounds like a bad employer kind of thing. I don't care if you're sick. Just get over it and move on. Okay. We can deal with some failures. Distributed systems experience real failures all the time. And so we learn to deal with these failures, embrace them, overcome them. And this is a very powerful technique that you will see over and over again. Checkpoints, logging. And you have a better understanding now of what the trade-offs are and why checkpoints are sometimes fine. And it's really time bound. The very thing that made FLP break down, which was there's no time bound on the delivery of messages, ends up being the factor that we care a lot about when we're making decisions on how to implement our distributed systems. We're not willing to wait forever. So your costs are associated with balancing performance at runtime. This is actually one of the things that I'm contributing in this slide deck because this is something that nobody else talked about. We talked about checkpoints. Checkpoints are potentially expensive as they get large. We talked about logs. Logs are potentially expensive as they get long, kind of that size thing. And when we talk about expensive, we're talking about how much time it takes. We want to be able to recover really fast. When I wrote the journaling system for episode 30 years ago, it was, the question I would always get is, so how long does it take to run FSCK? And the answer was, you don't have to. People had this whole mental model of you had to scan the entire drive in order to fix the file system so you could reboot. And it was like, normally you don't even notice it. We just do it during your mount. We restore everything. And it was a complete paradigm shift for people to really think about that at the time. Because people were so used to having their file servers down for an hour. The idea that it could take a second for you to restore things because we had a journal, we had a log. We didn't have to go and check all of our data structures to make sure that they were consistent. So at any rate, there are lots of costs associated with this. We have to worry about compute, storage, network usage. There's lots of trade-offs. Those become engineering challenges. They are not necessarily conceptual challenges. It doesn't make them easier. In some ways, they're harder because you can build the most beautiful, elegant system, and if it performs horribly, no one will use it. And you won't be employed. Checkpointing and logging are key tools here. We're going to build on top of this. We're going to look at more complicated consensus algorithms, but underneath the covers, what's generally going to be happening is we're going to be logging. We're going to see where we're going to distribute logs around and why we do that. And now you have a better understanding of what the trade-off there is. I can send a whole copy, we'll do that. I can send incremental updates, we'll do that. And we'll do mixtures of those things. And that's it. Questions? Very quiet class today. I know, it's snowing out. You're thinking about going out and rolling in the snow and making snow angels. No? What else do you do with snow? I know. You cut down, well, you start a bonfire and you put some marshmallows at the end of a stick and you roast them. That's a very North American thing to do. All right, thank you very much. I will see you on Thursday.